particular chapter, we're going to discuss and demonstrate two different parts of the system, the link ratio techniques module and also the corresponding module, which is called extended link ratio family, where you calculate ratios in the regression framework and you also extend them to find out whether the features in the method correspond to the features in the data. So I'm going to open a database and we are going to look at the triangle group, and this data is widely published and it's called MAC. It's incurred data array, so let me open it, and we'll go to ILC. If you wanted to look at the data, that's what the data is. It's American Reinsurance Association, I think Faculty of Business. It's published, and if we wanted to apply link ratio techniques to it, we just go to the LRT module, and you'll notice that we have windows within windows. So if we use the vertical outer scroll bar, we can scroll down to see the various other windows. If we click on the data ratios tab, we have the data and then the ratios. If we click on the ratio selection tab, we have the ratios and the selections. If we double click on selections, the title, the word, we're just looking at that window. The chain letter selection is what the Europeans call volume weighted average. We have arithmetic average, geometric average, the various types of averages. By default, the final selection here, second last row, by default it is the chain letter averages, volume weighted averages. If you want to select the arithmetic average, just double click on that line. If you want to select on this particular number, 1.1080, you double click on that. You can also select from the ratios table, suppose 6 to 7, 1.0264. You can select from the graphs. Let's go to the graphs. Now, the final selection is in black. Let's suppose I select this pink, so it turns out to be black. I can save selections. Let's call this junk. Save that. I can calculate averages which are not the last 3 or 4 years. I can do averages the last 5 years. 3 different types of averages. I can do that too. I can forecast. Also include inflation discount rates. And I've used ratios and cumulative data to do projections, but of course you can also project any incrementals. You also have another table which is Barnhart-Ferguson and expected loss ratio. But by default, because I do know the premiums are all set to 1, by default, which this is an input, premiums are input, expected loss ratio is actually input. I like data. Well, that's been set to 100%. So the expected loss ratio method, obviously because I used premiums of $1, give me ridiculous answers. The link ratio method, that's based on the link ratios I selected, and then you have the Barnhart-Ferguson. Of course, I can go back to the triangle group, and if I like, run the model junk. Oops, wrong place. This one here, I run the model junk. Now I've actually got 2 tables that are open. This is the first one, this is the second one. In the second one, I might decide to select the chain layer averages. Oops, that's the wrong one. Well, anyway, let me select the chain ladder averages. If I select the chain ladder averages, save that as chain ladder averages or volume weighted average. I save that, and I can compare it. I can do the forecasting, and I can compare that forecast summaries of Barnhart-Ferguson, and I can compare that with what I've got on the other side. Okay, let's close one of these. So actually you can run a number of models simultaneously on the same array and compare them. You can save the models, and you can always rerun the models from the triangle group. Or you can actually load a model from load model here. Okay. Now what's a ratio? So we're going to do a little bit of mathematics. It's not particularly difficult. A lot of this, well, in fact most of this, is actually covered in the paper Best Estimates for Research. So some of the work we're going to be doing is covered in that paper. Even the examples, the actual data examples, real data examples. Let's suppose we have a cumulative array of numbers. It could be reported claims, closed claims, whatever, paid losses, incurred data. In this case it's incurred. As long as it's cumulative. The Y values, we've got two contiguous development periods. The Y values are here, so Y1 up to Y12, and then X1 to X12. So this is Y1, this is X1. Let's suppose that this number pair was X1, Y1. Let's now calculate the ratio. The ratio is this number divided by this number. So the ratio is just the slope of the line between the origin and the number pair. In fact, every ratio, let's calculate another one. Y7, X7. Y7, for example, X7 is the slope of this line. So every ratio is just a trend line. An average ratio is an average trend line. So for example, an average trend line, which you could do perhaps on graph paper, this could be an average trend line, the one here in black. If you wanted to leave out all these points when you want to calculate an average ratio, you just fit a line to these points. You can do this in graph paper. Well, that average trend line, or average weighted trend line, is actually an average ratio. That's what an average ratio is. A trend, a ratio and a trend are the same things, and an average trend is the same as an average ratio. So now, let's try and see if we can formalize what we're assuming about the data. Let's assume now that given X, the cumulative of one development year, the average value of Y, the cumulative at the next development year, lies on the hypothetical average ratio line or average trend line. Given X, the variance of Y around this average ratio line is proportional to X. So I'm going to set delta equal to 1. So let's go back and review our assumptions. Given this value of X, that's the average value of Y. Given this value of X, that's the average value of Y. The other assumption is, given X, the variance of Y around the line increases with X. It's proportional to X. If you make those two assumptions and use weighted least squares to find the best weighted least squares line, you get the volume weighted average, or as the Europeans call the chain ladder ratio. If you now set delta equal to 2, where you're assuming the variance is proportional to X squared, you get the arithmetic average. You might remember that in statistics, a weight is a reciprocal of variance. So as I vary the variance, I'm varying the weight. So now we can actually generate averages, average ratios, by doing regression. So let's do it that way. So what you do is you go back to the triangle group, you highlight the triangle, and you go to ELOF. And by default, we've just calculated the volume weighted averages. And let's just check that that is the case. Go to selections here. Oops. And now let's compare this column with these red numbers in the spreadsheet type format on the right side. 2.99994, 2.99936, 1.6235, 1.6235. But on the left side, we did regressions, all these pairwise regressions. We took the first pair of development years, did a regression. Next pair, did a regression, and so on. And all we're really doing is replicating the volume-weighted averages. If instead we'd like to calculate the arithmetic average, we set delta equal to 2. And now the column in the regression table will correspond to the second row in the spreadsheet type table. So we can calculate different types of averages, or leave out observations, by doing regressions. And for that reason, really, we don't need this module in the system. So we're going to close it. And let's go back and calculate the volume-weighted averages. So we're back to volume-weighted averages. After we've calculated the volume-weighted averages using regressions, we can do some other calculations. For instance, we can calculate what I call residuals. And residuals, you'll see later on, actually serve two purposes. They're interpreted in two different ways. Let me erase this. A residual is an observed minus fitted. So it's the difference. What can we do with these residuals? We know the location of the y value in our triangle. Therefore, we can map or graph the residuals. We can graph them versus development year, versus the accident years, versus the calendar years, the diagonals, and also we can graph residuals versus fitted values. Let's do that. So we have four graphs. The residuals versus development years, the residuals versus accident years, the residuals versus calendar years, and the residuals versus fitted values. If you want to highlight this particular point, it's red now. That point is in accident year 82. The development year is 1. Therefore, the calendar year is 82 plus 1, which is 83. And that's its location versus fitted values. Now, if a model has the same features as in the data, then these four residual graphs should look random. But you'll notice that they're not. If you look at the residuals versus fitted values, you'll notice a downward trend, in fact, a very strong downward trend. So the method we've just used overfits the big values and underfits the small values. And in a couple of minutes, you'll see exactly why, just from the graph of the data, why the method is doing something which is not in the data. It actually assumes something about the data, but that is not a property of the data. Another thing that you'll see, a phenomena of this particular method, of this volume-weighted averages applied to this triangle, the method we've just used underfits the accident year 82, but overfits slightly the calendar year 84. Well, let's go look at the raw data. So this is the plots of actually the incurred data in 3 directions. If I do a trace for, well, before I do a trace, let's find out which years I need to do it for. The year 82 we overfit. Let's look at the data for 82, and you'll notice the data for 82, sorry, the year 1982 we underfit. Observed minus fitted is positive. That's because the data in 1982, the incurred development versus development year is low relative to the other years. 84 we overfit. Why is that? We overfit 84 because the 84 development is actually high. So a year that has high values, we overfit. A year that has low values, we underfit. And you'll be able to see that in this picture again. The high values we overfit, the low values we underfit. Now you'll be able to tell me why. If I were to ask you to fit a line for all these points, but you didn't confine it or restrict it to go through the origin, where would you put that line? Well, most of you would probably put the line, if you're allowed for an intercept, probably around there. Now, can you see the difference in structure? Line 1 assumes that the data goes to the origin. But if, in fact, the data requires a positive intercept, you can see now why line 1, method 1, chain ladder ratios, arithmetic averages don't matter, overfit the big and underfit the small. Line 2 represents a very different structure in terms of what's going on in the data. You're now going to say, given this value of x, that's the average value of y. Given this value of x, that's the average value of y. Line 2 has a much lower slope than line 1. So for method 2, line 2, you're now going to argue as x changes a lot, there isn't that much variation in Y. Okay, well, why don't we graph the data? So this is the graph of the data, development year 1 versus development year 0. Remember, each one of these is a ratio. That number, that distance, divided by that distance is a ratio. The red line is the ordinary least squares line for the origin. The green line is an ordinary least squares line that also has an intercept, an extra parameter. Now you can see that you definitely need an intercept. But it's not just more, it's actually more than that. The line for the origin, if we were using volume-weighted averages, would make two assumptions. One, that the line goes to the origin. The other assumption it makes is that the variance is proportional to x. But yet if you look at the points around the green line, the variance is not proportional to x. It doesn't seem to increase. It seems to be, in effect, just diagnostically, pretty stable. So there's only two assumptions in that method. Volume-weighted averages, it's in the method, but it's not in the data. Remember, a model is supposed to have the same features as the data. If you go to the next set of development periods, the next pair, you also need an intercept. So it seems like you always need an intercept. So what we do now is we go to model templates, and we're going to estimate both an intercept and a slope, or a ratio. So we go to model templates, and we do both an intercept, yes, a ratio, or slope, yes, okay. When we do that, you'll see that all the intercepts are positive. The last two pairs of years, they don't contain enough data to estimate both parameters. So all the intercepts are positive. If you look at the residuals versus fitted values, now let me clear this, Mark. They're straight. Let's go back to ratios to the origin. Overfit the big, underfit the small. Let's add an intercept. It's straight now. Now let's look at the excellent years. Ratio to the origin. Underfit, overfit. Include an intercept, and it looks straighter. All right. What's the next step in our model building? So Murphy, in 1994, suggested that we should include an intercept. And you can see for this data, we definitely did one. Otherwise, the model doesn't carry the features in the data. Now, if we look at this equation, which we just fitted, if you subtract x from each side of the equation, you obtain y minus x equals a plus b minus 1x. These two equations are equivalent. They're identical. It doesn't matter which one you solve in your spreadsheet, you'll get the same answers. But now y minus x is actually the incremental. So if I want to project the incremental at the next development year, I take the cumulative, multiplied by the ratio minus 1 instead of the ratio, and possibly then add an intercept if 1 is required. Now, in fact, the way this equation should be written out, the focus really should be on the second equation, not the first one. You know, when you use ratios on cumulative data to predict the next development year, you're not really predicting the cumulative. You're predicting the incremental, because you know the current cumulative. You're just predicting what you have to add on to the current cumulative. So in fact, in this equation, maybe we should call y minus x just p, say. The incremental in the next development year equals a plus b minus 1 x, the cumulative of the previous development year. All right, and that's the equation we really should focus on, even though these two are equivalent. Let's suppose now, for the sake of argument, you have your cumulative array and the corresponding incremental array. If these are y values and these are x values, then these will be y minus x values. Okay, suppose you find out that b is greater than 1 and a equals 0. In other words, it goes through the origin. How do you do projections? You'll take that x multiplied by the ratio to project the corresponding cumulative here. But if you multiply by the ratio minus 1, you'll project the incremental in the corresponding incremental in the incremental array. What if instead you find out something different? Incidentally, of course, if a doesn't equal 0, you just add a to each side. What if instead you find out that B equals 1 and A doesn't equal 0. Now what does that mean? Let's look at this equation here. If B equals 1, B minus 1 is 0. So to project the next year's incremental, I take the ratio minus 1, which is 0, and multiply it by x. Well, it seems like it doesn't matter what x is because I'm going to multiply it by 0. Let's do a graph. We are saying that if you graph these incrementals versus these cumulatives, the slope of the line is 0. There's no correlation. They're not related. That means that ratios have no predictive power whatsoever. That's what it means. It means you also abandon them. They don't predict anything. It also means something else. If you look at the reduced model, you're saying that an incremental equals a mean value plus a random part. Let's assume that the variance of the random part is constant. So you're saying these incrementals come from a distribution with mean A. The ordinary least squares estimate of A, the regression estimate of A, is the sample mean. So your projection here of the incrementals would be just the sample mean, the average of these incrementals. So this approach actually distinguishes between two ways of projecting your data. Do I take the cumulative, multiply it by the ratio minus 1, add an intercept to project the next incremental, or do I multiply by the ratio, add an intercept to project the cumulative, or do I abandon ratios at all, completely, abandon the previous cumulative because it has no relationship to the next column of incrementals, and just use these column of incrementals to project these incrementals by taking the average? Of course, we are assuming that the reduced model, where this term is 0, is actually true for the data. In other words, if there was a trend here, this model, reduced model, where you just took the average, well, that wouldn't make sense either. Okay, well, let's see what's going on. This is the graph of the cumulative versus the cumulative, and you can see that you need an intercept. But if you look at the incremental versus the cumulative, there's no correlation. That means from development year 0 to 1, ratios do not predict anything. Another way of stating this, if the previous cumulative is high or low, for instance, let's go back. If the previous cumulative is low, it doesn't mean that next year's incremental is low. If the previous year's cumulative is high, it doesn't mean that next year's incremental is high. They're not related. Let's go to the next pair of development years. No correlation, no correlation, no correlation. So there's never any correlation between the incrementals in a particular development year versus the cumulatives in the previous development year. And for this reason, if you look at the regression table, all the lines are pink, telling you that all the ratio minus 1s are insignificant. There's no evidence that the ratio minus 1 is not equal to 0. If I optimize, the system automatically sets all the ratio minus 1s to 0, or the ratios to 1, and only estimates the intercept. What are we doing when we estimate the intercept? We're calculating averages of incrementals, and we're using that as our projections here. Okay. All right. So for this data, ratios do not have any predictive power, and you're much better off just taking the average of incrementals, going down each column. Let's look at the three models now. Ratios through the origin, ratios through the origin, which make assumptions which are not contained in the data. For instance, the ratio doesn't go through the origin. You need an intercept, and the ratio doesn't have any predictive power. Next model, add an intercept, and the residuals are much better. Then if you set the ratio minus 1 to 0, the ratio to 1, if you've got a line where the ratio is approximately 1, if you set the ratio to exactly 1, you will hardly change the intercept, the estimate of the intercept. So now, if we only do what we call intercept only, slope or ratio equals 1, we call this the Cape Cod, the residual structure should remain pretty much the same. Let's go to ratios. Now, I might have mentioned in chapter 1 that if a model has features not in the data, and the data has features not in the model, all the answers based on the model are meaningless, just like all the answers based on tossing a coin are meaningless for a roulette wheel. It's the same here. So all the forecasts that I'm going to do now are meaningless. We've got the incremental forecast, we have the cumulatives, we also have a forecast summary, and in the forecast summary, you'll see that the coefficient of variations along the accident years actually increased more recently. And the reason, I mean, when you go from development year and accident year, so in 1989 to 1990, you're just forecasting another observation. Why is the actual coefficient of variation increasing from 59% to 150? Because the model you've just designed has not related the numbers in the triangle in any meaningful way. For instance, the model doesn't tell me any story about how the incrementals in the first development year are related. Are they random around a flat line? Are they sitting on a trend? In fact, when you think about the model, when you come out with your answers, it's information free. It doesn't tell you anything about what's in the numbers, apart from the fact that in this case, it has no predictive power whatsoever. Okay? If we estimate the Cape Cod, which is a much better model, when you look at the residuals versus the accident years, they seem to be flat. When you do the forecasting now, and you go to the forecast summary, you notice the coefficient of variations now reduce because you are relating the numbers in the triangle in some meaningful way. What assumption are you making about the numbers? You're saying that when I go down a column of incrementals, they're random from the same distribution, so you are relating them. When I go down this column, they're also random from some distribution. So this Cape Cod model, where only it calculates the intercepts or the averages of every column, does relate the numbers in the triangle in some meaningful way, was that ratio methods didn't have any predictive power and doesn't tell you any story about what's going on in the numbers. And you can see that I'm pretty passionate about this, and there's so many proofs of why ratio methods just don't work and don't tell you what's in the data. Now, let's go to the next step. There's a cumulative array, there's an incremental array. Suppose both arrays are adjusted by the same exposure base, some of your favorite exposure base. It's not important at the moment what it is, because this is what I'm not going to get to. I'm not going to get to that. Okay, I'm going to do something else. After you've adjusted your data, you look at this column of incrementals, and you graph them versus the accident year. W is the accident year variable or argument. And you look at them, these numbers, and they sit around a flat line. They're random around a zero trend line. I call that condition 1. So let's suppose now this development year satisfies condition 1. If you now graph this development year, these incrementals versus these cumulatives, I can guarantee to you there will be no correlation. The ratio minus 1 will be 0. In other words, for data satisfying condition 1, what's that? The graph of the incrementals versus development year sits on a zero trend line. You'll find out that ratios have no predictive power. Suppose now instead condition 1 isn't satisfied for your data, even after you adjusted for your exposure base. Instead, these incrementals are actually growing along a constant trend. What are you going to find out then? Most often, but not always, you'll have to find out, most often, but not always, if these incrementals are increasing, the cumulatives in the previous year will also be increasing. So when you do a graph for one versus the other, you'll see, say, a trend, say, suppose a constant trend. And when you try that model, therefore, you'll find that the ratios have some predictive power. So under condition 2, not condition 1, under condition 2, ratios will have some predictive power, especially if you include an intercept. But suppose now under condition 2, you're going to fit the constant trend. So you're going to add another parameter. W is the accident year argument. Let's review again. So there's a constant trend in these incrementals. They go up. a constant positive trend, you're going to include it in your model, and an intercept, and a ratio -1. So you have all three terms now. What's going to happen in practice most of the time? Most of the time, the trend will have much more predictive power than the ratio. And when you have the trend, the ratio -1 will go to 0. You will not need it. I'd say that's 90 to 95% of the time. Another possibility, of course, and it does happen on occasions, is that the ratio, especially when you have an intercept, has more predictive power than the trend. And when you use the ratio, the trend actually goes to 0. So use the ratio then. Another possibility is it's both. But let me remind you, most of the time it's just the trend and you don't need the ratio. Let's go back to this data and now estimate trend and ratio and optimize twice. And if you look at the regression table, well, the ratio -1 are all 0. The last 2 years we can't estimate both parameters. But in development year 2, there must be a trend. But the ratio -1 is still 0. So let's look at development year 2. You can see that if you graph the incrementals in development year 2 versus the exit year, there is a trend. It's not constant, but there is a trend. That the incrementals versus the previous cumulatives, no correlation. So for this particular triangle, development year 2 satisfies condition 2. So for development year 2, we have that condition. But for development year 2 versus 1, that still has no predictive power. In other words, these incrementals are not correlated to the previous cumulatives. I told you usually they will be. And if they aren't, anyway, the trend will have more predictive power. In this case, they have no predictive power even on their own, even though you have condition 2 satisfied. Okay, so just a quick summary of these various conditions, which are mutually exclusive. You take any real triangle that you've adjusted by an exposure base. You have the cumulatives and the incrementals sitting in Excel. And in Excel, you can draw some graphs. Let's suppose you find out that for a particular development year, condition 1 is satisfied. Then also, when you graph the incrementals versus the previous cumulatives, you'll find out that the ratios have no predictive power, or the ratio -1 equals 0, then you're much better off at just calculating the average of every column of incrementals. But you'd be better off doing that. But you're still not really all that well off because you're treating every development year as a separate problem. When you get to the tail, you'll calculate the average of 3 values and 2 values, then 1. But actually, the development years belong to the same problem, and they must be related. So this model in ELRF that just calculates the averages, which is much better than the ratios for this example, is still not a good model. Okay, suppose you have data that satisfies condition 2. What are you going to find out then? If it satisfies condition 2, very often the ratios will have predictive power, but the trend will have much more predictive power. The trend will have much more predictive power most of the time. What about if you've got data with condition 3? Well, what is that? Most data sets do not satisfy condition 1. Most data sets do not satisfy condition 2. And even if they did, by just taking the trends down the development year, that's not a good approach necessarily either, because you're treating every development year as a separate problem, but it's not. Okay, most data sets satisfy condition 3. What is that? If in the incremental array along the calendar years there's a trend change, then it's an axiom that this trend along these, for this development year along the accident years going down, is not the same as this trend. This trend is not the same as that trend. We call that condition 3. That's explained in the paper Best Estimates for Reserves. Indeed, if you look at the CIS syllabus, Subject 6, one of the objectives of that course is to learn the axioms of trends in the 3 directions. and we're going to do this in the next chapter. Bear in mind, these are axioms like 2 plus 3 equals 5. They're axiomatic for the data, therefore they'll also have to be axiomatic for our models. Otherwise, the models will not capture what is in the data. So let's review the 3 assumptions again, which are mutually exclusive. First one, going down, 0 trend. Second condition, 2, is a positive trend or a negative constant trend. Either positive constant trend or negative constant trend. And the third condition, well, that trend isn't equal to that trend because there's a calendar year change, and something we will deal with in the next chapter. Again, if you had data with condition 1, the best approach in the extended link ratio family is just to calculate the averages. If it satisfies condition 2, best approach will be doing the trends again, abandoning the ratios. But that's not necessarily a good approach because you'll be dealing with every development year as a separate problem. Okay, so this is the end of this chapter. In the next chapter, we're going to look at how do we deal with condition 3, and moreover, how do we actually measure the volatility in the numbers, not just the trends, and that is paramount. Thank you.